Good morning or good afternoon, depending on where you are. We are continuing with our thermodynamics lectures. My name is Professor Duke Orata. Today we still want to look at heat transfer in composite systems. And so we are going to look at heat transfer in composite system where we have a wall as a barrier between two fluids. Composite systems. Remember, those mediums are not the same. The wall is not the same in composition as whatever fluids you're talking about. So we have looked in the past at some of those heat transfers, and we are continuing this particular case where we are dealing with a case where we have a wall as a barrier between two fluids. So I want to consider the case of a wall as a barrier between two fluids. So that if, for example, we draw that as our wall, and remember, because you're going to use Fourier's heat laws, we are talking about this being perpendicular to the axis. Let us call that x axis. And let's say we have fluid this side, is the wall, is a barrier, and then we have our fluid. Then we have our fluid. Now, we got to think of several things. That means, one, there's an interface between the fluid and the wall. There's an interface between the fluid and the wall. Between the fluid and the wall. And the other thing which we need to know is that when you are next to the wall, that is, when you are next to the wall, let us take some theoretical stagnant layer next to the wall. This is a layer, let's call it sigma x. That's a stagnant layer next to the wall. If we look at the temperature profile from the wall as a function of that displacement, then we will have this kind of profile. There will be significant change. There will be a significant change in temperature with displacement next to the wall. There will be a significant change in temperature with displacement next to the wall. And of course, remember that significant change, we talk of heat transfer resulting from temperature differentials. And so there will be a significant change in temperature with displacement near the wall. So let's just note that there will be a significant change in the temperature gradient. Near the wall. What are we talking about? That is dt over dx. Let's call that a wall W will be significant. will be significant. So let's mark that W. And as you go further away from the wall, as you move further away from the wall, then convectional forces start impacting. So convectional forces start impacting again. So we are saying here we have dt over dx, the wall W. So as you move further away, then there is gradual drop in that gradient. The change is not as rapid because in this region now, we have convective forces which help in the diffusion of thermal energy. So there are convective forces. So as you move away, you move further from the wall, convective forces effectively diffuse the thermal energy. In other words, remember we say that when we are dealing with convective forces, several things come into play. Heat transfer in liquids, we say normally can be through forced convection, where, for example, you pump a liquid through a heat exchanger, or natural convection. In this particular case, we are not dealing with compressors pumping liquids through heat exchangers. We are dealing with natural convection. We are dealing with natural convection. And natural convection, several factors can play a key role. There's density gradients, play an important role. Velocity, fluid velocity play an important role. Viscosity, etc. all play a key role in that area. And so you see that the dispersion is not as next to the wall. So that if we add an axis here, then we can say it's our temperature axis. In theory, let's say that's our temperature axis, that's our x axis. So this is the profile. Let's leave that as the profile, temperature profile. So we are near the wall and we're in this particular section. I want to mention that it is very, very important to remember that the kind of wall we are dealing with here, that interface, is behaving in the manner it is behaving because it is basically a neutral wall. We can have, it is good to take cognizance of the fact that we can have in cases, and you must always know that the behavior will not be exactly the same as that. I just want to point out, it's very important to take cognizance of the fact that this surface here is neutral. If we are talking of an electrified surface, where we have the interface, so the interface between, in that particular case, the electrode and the solution will be completely different from case of a neutral surface. And so it's good to know that if, suppose this was an electrode surface and we had a solution, then you'd have what is called the double layer. So in electrified surfaces, we'll see double layers. interfaces, we have double layers. And that's in passing. So if that was an electrode which is charged, then we would have what's called the inner Helmholtz plane, that's IHP. We would have the outer Helmholtz plane, and you'll have what's called the diffuse double layer. Very important. Note that these surfaces, the interfaces, depend on what kind of surface you're dealing with. And so when you're dealing with materials which are like conducting polymers, then the double layer will become very, very significant. So this is significant. This is significant in electronically conducting materials. That's very important for us to note. So when you have a neutral surface, the system is pretty stable. The system is pretty stable, other than the convective forces which we encounter in these sections here. Convective forces. And they play a critical role in the diffusion of thermal energy. Now, let us look at this, our neutral surface, in light of Fourier's heat law. Let's look at it in terms of Fourier's heat law. So if you let's apply the Fourier heat laws to that neutral surface. The neutral surface, this what we called the barrier. Now, in this section here, next to the wall, next to the boundary or wall, we are going to have the heat transfer in terms of Fourier's heat expression as minus, let's call it Kf, let's have A there, and of course we have dt over dx, and we have marked that as next to the boundary where our W stands for wall. Always remember that. So we are calculating our W stand for wall. And so, assuming that we don't want the surface area, in this particular case, we can factor it in and have our Q over A, which is Q, to be equal to K minus Kf dt over dx W. And so, that is next to the wall here. That is next, that's expression next to the wall. As we move further away from the wall, then like you have said, these other forces which have ability to disperse this thermal energy so that the system kind of quickly equilibrates, attains some sort of thermal equilibrium easily, cannot therefore be represented in that manner. So further away from the wall, further from the boundary, then we can say Q, which you know is heat transfer per unit area there, will be given by minus Hc, and we will have the temperature in the solution down there minus the temperature next to the wall. So we are defining now HC as convection heat transfer coefficient. And TS, temperature. In the solution, in the fluid, far from the boundary, boundary wall. And we can say TW is the temperature in the vicinity boundary wall. So we are just applying note one, that the significant temperature gradient next to the boundary. And as we move into solution, we have that region where now convective forces start taking charge in terms of dispersal of the thermal energy. So whether it's density gradients, viscosity, velocity, and so forth. If the surface is electrified, that region is almost referred to as the diffuse layer. They are not exactly similar because they are additional forces. When you're talking of electrified surfaces, there is a force which is basically applied, and so we don't want to look at them a little bit. We look at them a little bit differently. So even if we have the diffuse double layer in that region, that is not the same as this region here where convective forces take place. But there's a latitude of freedom of behavior as you move far away from the interface, So that latitude of behavior will depend on whether you're dealing with a charge system where electrical forces and so forth are also still included in addition to convective forces, or you're dealing exclusively with the neutral barrier where electrical forces are not involved. They're just thermal forces which are basically involved, and convective forces play a big role in that dispersal of the thermal energy. Now, once we have this expression, we now don't need this. We now don't need that. So we can say, therefore, it is clear that minus K FA minus KF dt over dx, the wall is equal to minus HC into TS minus TW. TS minus TW. So that if we rearrange these quantities, very simple rearrangement. So if we just, of course, the negative signs will have cancelled, then we can divide by HC and divide by that slope there. So we have KF over HC being equal to TS minus TW over dt over dx W. So this difference in temperature, let's call it D, and put an asterisk there. So that you have dt over dx W. Note that dt, don't forget dt, mark that asterisk, you have defined as being the difference between those two temperatures. And so you can clearly see that if you do dimensional analysis, on that expression there, so if you do dimensional analysis on this expression here, so do dimensional analysis, then you see that Kf over Hc will we'll have dt, and then of course, and we have dt, we have dx, we have dt. So that you actually are able to cancel them out in your mind. And so Kf over Hc is equal to this quantity here, which we call sigma x, that is the stagnant layer, which we had marked as the stagnant layer next to the wall. Remember that? The x-axis, we have said that that represents the stagnant layer next to the wall. The stagnant layer next to the boundary wall. Very important for us to know. So that the ratio of these two coefficients clearly will determine this stagnant layer next to the wall. In other words, if this convection, that's convection heat transfer coefficient here, is large. If Hc is large, much greater than Kf, then sigma will be small. In other words, if this is much greater, then that layer next to the boundary wall will be much smaller. And of course, if it is much greater, if it is much less than Kf, then sigma x will be large. So remember Kf is a thermal heat transfer coefficient, and the other one, Hc, is a convective transfer coefficient. And so remember, when H is great, that means the convective forces are much greater. So of course they will disrupt this layer. Convective forces, density, gradient. So there will be movements back and forth, viscosity, velocity. So basically this will be a mixed up, a diffuse layer. Diffuse layer, synonymous with that in the electrified surface. But then when Hc is much smaller, then of course we have this stable and large layer, stagnant layer next to the boundary, and so sigma x, we will have a large stagnant layer next to the boundary, that is the sigma x will be large. So it's interesting, these interfaces are very critical. These interfaces are very critical in terms of fluid dynamics. Very important in terms of fluid dynamics. So let's stop at that point. We are continuing with our lectures on these heat transfers.